this is the Milky Way globular clusters in terms of the size, and this is what you get for this galaxy. It's peculiar. And also something which, no matter at what distance you put it, will remain a puzzle, that the shape of these globular clusters, they're not as spherical as you would expect on the sky from our own Milky Way. So that's the thing. So when I saw this, the total mass of the globular cluster is 10 to the 6. And in a halo, which is about something like 10 to the 8 and the 9, according to the original paper of the observer, which proposed this galaxy with dark matter. This is, by the way, this ratio is also off the charts compared to other things. But it's used, this ratio between the mass of the globular cluster to mass of the halo is about 10 to minus 5, in, roughly in all galaxies. Dynamical friction should be important. So I did the calculation for dynamical friction, and I will not, talk about all the details here of the simulations and things like that. I just want to point out that dynamical friction is something we should think about in these things, because these galaxies, these globular clusters, we may well have a problem with dynamical friction there. They should have sunk to the center, but we see them far away from the center, at least some of them. The situation is not strange. Fornax actually has 5 globular clusters like that, or maybe 6, and they're supposed to sink to the center. They're not sinking the center. And let me even demystify this. These guys, Angus and my friend Antonaldo de Ferrio, have proposed long ago that perhaps the globular cluster started from a much larger distance than we think. And I spoke to Antonaldo. I told him, are you happy with this? He said, no, it just, I just proposed that because, not as a solution, but as something which people, as a curiosity, because we still do not have a model, a scenario for how these cluster could start very far from the galaxy. So he's aware of that. Now, in my paper, I actually included dark matter, a little of dark matter, not too much, and found what I found. So these guys, of course, I wanted to do it with stars. I didn't for some reason. These guys did it only for the stellar component alone. And they get actually very similar results. If this is the distribution, the observed distribution, this is what you get in simulations, which they have after they took into account the dynamical friction. However, it's very funny. Okay, they give me a compliment here, that's fine. I'm happy to take it. But then again, they give a list of shortcomings in a very strong language. Now, the serious shortcomings here are already discussed in my papers, and the others, frankly, they're not worth discussing. I'm not using strong language. If you read their paper, the language is stronger, so therefore I feel that I am entitled to respond in a strong language. And so they agree with me on the results, but they disagree with the conclusions. And their conclusions basically is that, okay, we just start with globular clusters which are far away than what we would expect or what you see by some factor. They don't offer any calculation of that. So basically they invoke the Angus and the Ferrier solution. Okay, so I'm actually finished, but I want to show you something, how we can get high mass for this galaxy. Okay, so we observe the globular clusters. But this galaxy is in the field of another galaxy, okay? So it's associated with a larger galaxy. And it's at a projected distance, something like 75 kiloparsec, if I remember, this is the, something like that. The relative velocity between the satellite galaxy, this DF2, the ultra-diffuse galaxy, and the group of galaxies, or the big galaxy to which it belongs, is about 293. So it's almost skimming, actually, because if you look at the circular, the line of sight velocities of satellite galaxies in this big galaxy to which the DF2 belongs is about 110. So it's actually our galaxy with little dark matter, or the clear dark matter, is skimming it Nonetheless, there is tidal stripping going on. And my model here is that if your original galaxy has the size of 15 megaparsec, this DF2, and then you strip everything down to 10 or 7 kiloparsec or whatever, then the material with large velocities crossing the inner regions is no more there. It's not there anymore. And this effect alone will give you global clusters with smaller velocities than you expect. And actually, here is what happens. If you don't strip the material, you get velocity dispersion of some original halo of 10 to the 10, not small halo, certainly close to what you do expect. You bring it down to this after stripping. So that gives you something which is quite in agreement with the measurements. And this is for just technical matters of how they do the modeling. So instead of having the dynamics of the kinematics over a cluster giving you mass which is here, it's giving you mass which is here, still far, it's not too far from what you expect from other galaxies. So that's fine. But then there was a challenge, is that actually now they measure the stars. The stars are well inside, they're protected from the tidal field, unless you believe Hammer, sorry, to practice my French, which is almost non-existent. Okay, so the M7 measure velocity dispersion for the stars at this value. So this is a high value, he says, and it's basically mitigates the problem of that there is no dark matter. But they use the diffuse, it's not very high resolution. And there was a paper by Van Dokkum's group, and they actually get sigma of stars of something like 8.4, and they claim that the controversy continues. Perfect timing, actually. So I devised that for this, I needed to work harder because tidal stripping is not enough. Okay, so what I said is that we know that supernova exists. This is a small galaxy, supernova feedback must be important, and let's invoke supernova. And actually, if you invoke supernova, basically the effect is very simple. If you cool the gas, so before cooling, just whatever you have, sigma is here, you cool the gas down to the inner regions where the stars are, so you enhance the velocity dispersion. That's not good, but then again, you want to get rid of the gas. If you get rid of the gas, then you reduce the velocity dispersion again to a level which is acceptable by the observations. So I'm invoking winds to actually do that, and this is, if you look at the gas content of this galaxy, then nothing is detected. So this is consistent with this. And I'm not offering a model for ultra-diffuse galaxies. There are models by Avi, by Dal Canton. That I'm just trying to explain the velocity dispersion here. And if you do that, you get actually the reasonable amount of dark matter in that galaxy. Final thoughts. So I like this quote from Shapley: no one trusts a model except the man, this is not politically correct, sorry, but it's not mine, who wrote it. Everyone trusts an observation except the man who made it. We should keep that in mind, actually. Broader scope than the standard model paradigm may be useful. And this is we do that in the dark sector. That actually could be a very good thing to think about. Large galaxy surveys are important. Cosmic variance, and this is a warning, cosmic variance in the peculiar velocity is very large, so when you do correlation functions like what many people do, actually you will get a biased result, just simply because we don't have a large sample of velocities. This correlation function has also been claimed to rule out Landau-Sidane. That's it. Thank you.
All right, it's great. Questions? You mentioned very briefly the 1700 kilometers per second claim, and you said that some people claim that it rules out Landau-Sidane. But then at the same time, there are supernova peculiar velocity measurements that are not as big. Would you like to comment? I mean,
okay.
How reliable is this claim? And
that are
Well,
supernova.
the claim that's of the 1700, given that supernova measurements of peculiar velocities are very modest.
Oh, sorry. I think I did not explain that well. The claim is not about 1700. The claim is that they actually measured the bulk flow.
Okay.
The bulk flow around us, and they got values like 400 instead, that while they should have got 200.
But not as
The 1700, this is when I actually looked at the data and I said, okay, let's find an example where things are grossly different from this. And I found that. I just averaged things. I wasn't looking for it in a serious way. So this luckily this claim hasn't been made in that sense. And you're right to point out that supernova actually give something which is consistent with lambda CN.
My intuition for these models that break the coolants maybe bad, but I'm trying to understand. You obviously focused on structures at the dwarf galaxy scale, but I'm thinking about at the galaxy cluster scale. And are there detectable changes here in terms of comparisons of lensing masses to dynamical masses?
Yes.
I would think that there would be.
Yes.
When normal galaxies fall in, as I understand it, their dark matter will start to get an extra tug, and if the baryons are massive enough, then they'll kind of tag along inside this. So I would think the galaxies would get heated, effectively enough with higher velocities.
Okay, so galaxies, so you're right in the comparison between lensing and velocity dispersion. Galaxies don't feel this additional force, they feel the actual mass.
But if their dark matter halo starts to run ahead of them because the dark matter halo wants to go towards the cluster center, then until that dark matter halo really
Right,
gets stripped
right,
away, they'll
right.
kind of
Right, so what happened, right. So this is, again, this is detailed